Hey guys, today we're going to be talking about the roots of quadratic functions. And the roots of a quadratic, they are the part of the function, part of the parabola that intersects the x-axis. So our roots, just another name for the x-intercepts. And then you also may see them called the zeros of the quadratic. They all relate to the same thing. It's going to be where you cross the x-axis. So it's always going to be x, comma, and at the x-intercept, or the roots of the zeros, that's going to be where our y value is 0. So as an ordered pair, it's always going to be x, comma, x, comma, 0. So whatever x is, comma, 0. With quadratics, we have 3 scenarios here. So let's look at our first scenario. First scenario, let's say we have the coordinate plane, just like this. X and y axis, and we have a nice little quadratic, and it goes something like this. We'll say we have a maximum right here. This would be an example of having 2 real roots. Again, the roots are the x-intercepts, also called zeros, so our 2 real roots are going to be right here and right here. I just kind of sketched this quick so we don't know what the exact values are, but you would just see where their x-intercepts are, and those would be your roots here. So that's one possibility. You could have 2 real roots. Another possibility, we have y and x. We'll go in blue. Let's say we have this quadratic, this little parabola right here, and it touches the x-axis at one specific point. This would be an example of having 1 real root. And there's a special name for this. We're going to talk about that in a second. And our last possibility, well, that's going to be, make a nice little small one over here. Let's say we have this parabola like this. It has a nice maximum right here. Since this is the maximum value, you're never going to go above that, meaning you never touch the x-axis. So this would be an example of having no real roots. So these are your 3 scenarios. You can cross at 2 points, you can touch at 1, or you cannot touch the x-axis at all, and that's going to tell you how many roots you have. And to say what the roots are, you would have the ordered pair x, whatever your x value is, comma 0. If there are none, you would say there's no real roots. And we're going to apply this a little bit now. See if we can recognize the roots in some different graphs. So one way you can find the roots is if you have a graph, you can just look and see where the roots are. So we're going to take this graph here. I have 3 of them. We'll start with the top left, the blue one. We'll go from left to right on the slides. So we're trying to find the roots of our quadratic here. So for the first one, it might be hard to see on the slide, but this is what it should look like. The important information. So finding the roots or the zeros, the x-intercepts, you're just looking to see where you cross the x-axis. Clearly we cross right here. Notice that that's the minimum value of this function. So our x-intercept or our root or our zero, all the same names for, or different names for the same thing, is right here, and that's the ordered pair 3, comma 0. X is 3, y is 0. So you could either say 3, 0, or you could just say the root is 3, the 0 is 3. By using that phrasing, by saying the root is or the 0 is, you're implying that that's where y is 0. So the root is 3, that means you cross at 0, 3. Our next one, we have this parabola right here. Notice how it opens downwards, so it has a maximum, meaning it's not going to go above this point. Clearly we don't intercept with the x-axis, so this one has no real roots. And lastly, we have the red graph right down here, our x and y axis. And for this one, we can actually say what the roots are. So let's look. We have our vertex right down here. So let's see, our axis of symmetry is x equals positive 1. So we're at 1, 2, 3. So one root is 3, 0. Another root is negative 2, 0. So you could list those 2 ordered pairs. You also could say the roots are negative 2 and 3. And if you're told the roots are -2 and 3, you should know that's talking about where you cross the x-axis. And just like that, oh, that's not 3, that's a 4. Sorry. So the roots are 4 and -2 for this one. Okay. And that's how you can do it with a graph. Now, kind of like we've talked about in the past, especially when we did like systems, the method of graphing to find solutions isn't always the best option because your roots might not be nice numbers. They might be like 3.28, and it's kind of hard to find that on a graph when you're using graphing. So another way to find the roots is actually something we've been doing, and we can do this or find the roots algebraically. I'll show you how to do a couple algebraically, and that's going to be the best method to get in the exact roots. But if you have a graph, that's what you should be looking for. Oh, before we talk about algebraically, I forgot about this one. So there is another terminology that's used when we have one single root. And let's say we have this parabola here. If we have one root, we actually call this, believe it or not, a double root. So when you have one unique solution, one real solution, we call it a double root because it's going to, the root is going to appear twice. So like here we have the root, let's just say this is -1. So our root is -1, 0. Maybe it came from the function y equals, and I'm going to write it like this, x plus 1 squared, because if you were to expand this out, you could say it's x plus 1 times x plus 1. You're going to end up with the same root twice, so it appears twice. That's why we call it a double root. It would show up twice. So there's only one root, but it would show up twice. It happens when you have a perfect square quadratic. Okay, so that's the terminology. Don't let it fool you. It means there's exactly one root. It's just that the root would show up twice. That's what a double root means. All right, let's do some algebraically now. So let's say we have f of x equals x squared plus 2x minus 80. So we could go through and graph this and look for the roots that way. It can be a bit of a pain, more time consuming, and you might make small little mistakes. But let's think about what the root is. The root is, the same thing as the 0, the x-intercept. It's where y is equal to 0. It's where your output is equal to 0. I have to fix the smiley face. So how can we show that the output is 0 here? Well, we would just set this side equal to 0. This is like y equals x squared plus 2x minus 80. And now all we're doing is solving the equation for x. What values of x give us the output of 0? And it's just like solving an equation that we did in the past. This is why factoring is a great idea. This is set up perfectly for factoring and to use the zero product property. If factoring doesn't work, it's also set up perfectly to use the quadratic formula to find your roots as well, which sometimes you might need to fall back on that. But to factor this one, let's try. We need to find a product of -80 that adds up to 2. Since the product is negative, one's positive, one's negative. And think of two numbers that are going to multiply to be -80, add up to +2. So adding up to +2, they should be kind of close to one another. And when you list these out, you'll come through and realize that 8 times 10 is 80. So one of them should be negative. Which one will give us a positive answer? Well, that would be if we had a -8. So -8 plus 10. Now these are close to being your roots, but we have to say what solutions or what values of x would make this equation work. So the values of x would be -10 and +8. So our roots are -10, 0, and 8, 0. Those are the values, those are the values that'll make this equation work. So those are the roots of this function. Let's go ahead and try our other one. This is how you can solve algebraically. And you could use the quadratic formula if you want to, but usually factoring, if it's possible, will be quicker and get you there a lot easier, and you won't have to do all these calculations. So we have the function Notice we're in standard form, which is great. If we want to find the roots, we're going to set the output equal to 0. So what value of x gives us an output of 0? And I noticed this is a perfect square, but let's say I didn't notice it was a perfect square. We're going to multiply to be positive 1, but we're going to add up to be negative 2. So it's a negative times negative. What times what is 1, but adds up to negative 2. You're going to realize it's negative 1 and negative 1. And you're going to end up with x minus 1 squared. We could just leave it like this. But we should recognize that our solution is positive 1 here. So our root to this function is 1, 0. And again, this is the double root. Notice how the same root pops up twice. So there you go, a double root, 1, 0. If you're feeling okay with these, you can go ahead and stop watching. If you want to stay on, I'll do a few more finding the roots by graphing, get some practice graphing, and we can see and kind of go through the thinking of when we're graphing how we can conclude how many roots there are. So if you're signing off now, have a nice day. If you're staying with me, then yay. So our next one, we want to find the roots by graphing. So here's our function. To find by graphing, we're going to need to find the axis of symmetry. Axis of symmetry is the opposite of b. So positive 4 over 2a. 4 divided by 2 is 2. So axis of symmetry is x equals 2. So it's going to be right here. And then we need to find the vertex. So for the vertex, notice we open upwards, so we're going to have a minimum at x is 2. We need to find y. 2 squared is 4, minus 2 times 4 is 8, so minus 8 plus 3. So f of 2 will give us, well, we should have negative 1. So there's our minimum at 2, negative 1, right here. We open upward, so we're going to definitely have roots here. We're going to have 2 of them. And let's find out where they are. We have a y-intercept of 3. So y-intercept of 1, 2, 3. We can use symmetry. So clearly our root is going to be somewhere in this area, somewhere in this area. So let's just check and see if 1 and 3 work. Make a little table here. Let's put 1 into the function. 1 squared is 1, minus 4 times 1. So 1 minus 4 is negative 3, plus 3 is 0. We have that y is 0. That jumps out to us because that's going to be the root. So there's one root. You can use symmetry to find the other root. And this is what the parabola looks like, or is supposed to look like. But the clear thing here is we're looking for roots. So one of them is 1, 0. The other is 3, 0. The roots of this are 1 and 3. Let's go on to our next quadratic to find the roots of. Our next one, we are graphing x squared plus 25 equals 10x. So in order to do this, let's go ahead and get everything on the same side. X squared minus 10x plus 25, say equals 0, but this is the function in standard form, so we're going to go ahead and graph that. So our axis of symmetry, take half of your b, which is, take the opposite of b, which is 10, and that's going to be over 2a, so you're taking half of your negative 10, and you have an axis of symmetry of x equals 5. 1, 2, 3, 4, 5. Now go ahead and notice that we are going to open upward, which means we have a minimum. So we're going to have a min at 5 comma something. Plug 5 into your function, see what the output would be. So 25 minus 50 plus 25 is 0. So there's your vertex, 5, 0. And really logically right now, if you know this is the vertex, and it's a min, that's the lowest point, and it's on the x-axis, that's going to be one root. It's a double root there at x equals 5. But if you want to continue to graph your parabola, you could use your y-intercept of 25, so way up here, and you're going to end up coming down. But right now we just want to find the roots. So our root is 5, 0. You could plug in some more test values to see where everything ends up, but our goal is to find the root, so our root is 5, 0. You also may notice this is a perfect square. That's an indicator that you're going to have a nice double root. Alright, we'll try the last one, and then I'll send you on your way. So our last one, let's go to red. We have y equals negative 3x squared minus 6x minus 8. Don't know if we can see that minus 8. Minus 8. So go ahead and find your axis of symmetry. Opposite of b is plus 6 over 2a is negative 6. So your axis of symmetry is x is negative 1. X is negative 1. And now let's find your vertex. Notice we open downward, so we're going to have a max. Max at negative 1, comma. Well, when you put negative 1 in, I'll do the work over here. Negative 1 squared is positive 1 times negative 3 is negative 3. Negative 1 times negative 6 is plus 6 minus 8. So when your input is negative 1, your output is negative 5. And that is a max. So negative 1, negative 2, 4, 5. This is a max value, meaning your parabola is going to open downward. And logically, right there, you can figure out you're never going to touch the x-axis, so there should be no real roots. You're opening downward, you have a max, you're never going to touch the x-axis. So you can kind of use what you know about the characteristics of the function to find out that there are no real roots. And that's all we have for today. You can go ahead and practice some of these. We'll see more applications of quadratics in the upcoming days. Have a nice day, guys.